because correlation and regression is not something that's just limited to statistics. Anytime you're looking to determine if there's a relationship between two variables, this concept comes into play. So we're only going to focus on linear regression and the extensions of that concept, because honestly, you could transform a relationship so that it becomes linearized, and then you could apply the same technique. So I'll show you how to handle something like that. All right. So we actually get these matrix equations from this relationship. So it's kind of like calculus gives us partial derivatives in Calc 3, which in turn gives us these rules that we use for statistics. And then linear algebra gets a hold of these rules and says, wait, I can represent these using matrix operations, so I'm just going to do that. Right? So either way, it's going to give you the same result. Right? The functions are built into your calculator, the linear regression, so you could actually check to make sure that your values are correct just using other techniques. All right, but what I want to do is I want to show you how these two tie together. So at this point, I'm going to show you how we get from the matrix equations to the Calc 3 versions of the equations. And then when we talk about partial derivatives, I'll show you how to go the other way. All right. So a lot of interesting applications coming up. So all we're really asked to do is determine the solution to these matrix equations. So you can see how we have the product of the transpose of x and x itself. And that result is going to then be multiplied by the vector AB. All right, so that's a place to start. All right, so I have x, which is defined as the column of all ones, and then the column x1, x2, all the way to x of n. All right, I want the transpose of that. So column 1 becomes row 1. So 1, 1, 1, skip a bunch, end with a 1. x1, x2, I'm throwing in an x3, skip a bunch, x sub n. We're going to take that and multiply it by x. All right, so x, again, is all that other stuff, but I'm going to rewrite just so I have a third one in there. Now, of course, my pen doesn't want to work. All right, so we have 2 by n in terms of the dimensions of this matrix. So 2 rows, n columns. And the other one is n by 2. So the result should just be 2 by 2. All right, so that's what this notation is telling us. All right, so that's what we're looking for. So we're going to have 1 times the 1 plus another 1 times 1 plus another 1 times 1 plus another 1 times 1. So when you multiply all that out and add them up, you're really taking 1 plus 1 plus 1 plus 1 plus 1 plus 1 n times. All right, so xt times x, the first entry of that 2 by 2 matrix, assuming it wants to let me draw a matrix, is going to be n. All right, and that's because 1 times 1, or I'll write a little bit simpler. 1 plus 1 plus 1 plus 1 n times will give us a result of n. All right, so it's basically a position counter. After the first entry, I have 1 value. After the second entry, I have 2, then 3, then 4, then 5. It's basically counting from 1 to n. All right. So then I want to do the same thing, taking all of this row of ones, multiplying it by this column containing x of 1, x of 2, x of 3, all the way up to x of n. All right. So what that's going to amount to is x of 1 plus x of 2 plus x of 3 plus x of 4 plus x of 5 all the way up to x of n, which is the same as saying the sum of x sub I going from I equals 1 to n. All right, just in shorthand notation, that's really all it's saying. All right, because I'm loosely using the term shorthand notation here. If I plug in a 1 here, I get x of 1. Plug in a 2, I get x of 2, then x of 3, x of 4, all the way up to x of n. All right. Now, when I take the second row and multiply it by the first column, I'm going to get the same exact thing. When I take the second row and multiply it by the second column, I'm going to get x of 1 times x of 1, which is x of 1 squared. Then x of 2 times x of 2, which is x of 2 squared, x of 3 squared, x of 4 squared, x of 5, all the way up to x of n squared. All right, so the notation form of that would be saying that I'm pretty much doing the same thing I did for the other ones, going from 1 to n, except it's x sub I squared. Now that's a whole lot easier than writing out an entire sum of products. And in fact, I would even argue that writing it with variable subscript of n is a lot better than a situation where, for example, I gave you x sub 13 as the max value of n. Because then you'd actually have to carry out the math. You don't want to do that. All right, so next up, so we have that part, that's great. Next up is the transpose of x, times y, all right? So I'm taking this and multiplying it by the y. So I'll make a little note. X transpose multiplied by y. All right, so the row of ones, so there's only two calculations that we need to do. Row of ones multiplied by the y's, going from y1 to y2, y3, y4, all the way up to y sub n, adding them all up, what that's telling me is that I'm getting, sorry, just make sure I put my dimensions right. Yeah, 2 by 1, okay. So the sum of all those y entries, so again, we're multiplying this now, from 1 to n. And then I'm going to be taking each one of these x entries in row 2 and multiplying by the corresponding y. So x1 times y1, x2 times y2, x3 times y3, all the way up to x sub n times y sub n. All right, so that's going to give me x sub I, y sub I. All right, so if you start kind of glancing back to the, well, this is really a streamlined form of the notation because I stripped it down and didn't put the bounds, I equals 1 to n, just because it gets a little too busy that way. But it really has the same structure. I got a sum of y, a sum of y, a sum of x squared, there you are, a sum of x, right now, sum of x, y. We have all the ingredients. It's all there. It's just the natural question. Okay, so how do you get from here to there? Right? It comes from this matrix equation because it's really this times AB that's going to give us that. Right? So unless you want to get into row reductions, which I don't think you want to do. I mean, I know you don't want to do. you're going to use inverse matrices in order to figure this out. All right, so what we're going to be looking at, unfortunately, means I have to rewrite it all. But I'm gonna strip it down because there's a lot of extra stuff here that I don't want to have to write every time. Now that we have the framework established, that looks like a negative set. Let me just fix that. Even though it's black, it still looks like it's negative. And there's no justification for why it would ever be negative, but I don't want that there. So I'm stripping it down. All right, so in solving this, I'd be looking at AB being equal to the inverse and we'll actually find the inverse in a second, of this matrix multiplied against the sum of y, sum of xy. All right. So obviously, again, don't want to use row reductions to figure this out. So what we'll do is use the shortcut for finding the determinant of a matrix because it's 1 over the determinant, and then you do the diagonal swapping and negating. Right? So what I need, because this is the transpose of x multiplied by x, I need the determinant of transpose of x multiplied by x, which is n times the sum of x squared minus a different kind of sum of x squared. All right, this one has just the x being squared. The diagonal up is the sum of x as a quantity being squared. All right, so those are two different things. Now, if you're glancing back and forth to the rule that's above, the Calc 3 rule, you'll see that this is an element of that. All right, so we're slowly getting there. All right. So just about 20 more minutes of work on this problem and we'll be there. Like 4 minutes. But I'll make it seem like 20 minutes. It's one of my talents. All right, so the shortcut for finding the inverse is swap the downward diagonals. Let me highlight those. And negate the upward diagonals. Then we have to multiply that by the sum of x, I'm sorry, the sum of y times the sum of y over the sum of xy. So the other vector. So not over as in a fraction, over as in physically over. Like how you feel about this problem. Okay. All right, I'm going to leave this alone temporarily. And I'm just going to handle this because that's just matrix multiplication. All right? But again, we're not really multiplying anything. We're just symbolically representing the product. All right, so we got a 2 by 2 against a 2 by 1. So we're looking at a 2 by 1 vector as the result. It's just going to be kind of a beefy 2 by 1. All right, so sum of x squared multiplied by the sum of y. All right, and then the negative sum of x times the sum of xy. So add that together. So it's really going to be minus the sum of x, sum of xy. All right, so that entire thing is the first term of the vector. All right, then I'm going to do the same thing with the other guy. So negative sum of x, sum of y. And then n, so plus n times the sum of xy. All of that multiplied by 1 over n times the sum of x squared minus the sum of x as a quantity squared. And that's what your AB will be equal to. All right, so this will be a scalar. We could rewrite this as A equals this fraction multiplied by this expression, and B equals this fraction multiplied by that expression. But all we would be doing is rewriting what we have above. All right, I'll just show you. I'll just glance to it very quickly. All right, so we have the sum of y, sum of x squared, minus the sum of x, sum of xy. All right, all over that denominator, which is represented out here. Then the sum of n times the sum of xy, which is right here, minus the sum of x squared. No, that's right. Okay, no, I'm good. No, I'm just so used to screwing something up that I was just surprised that I didn't. But look at that. That's a derivation. Which is kind of crazy to think about because we just spent 17 minutes or so. Well, maybe a little longer than that because I've been having this habit of forgetting to hit the record button. But we spent, let's say, I'll round it up to 20 minutes, deriving this relationship. When in reality, whoever came up with this, they started with that and worked in the other direction to come up with these factors. All right, so you got to think about that. I mean, this, we just did some multiplication. Well, we did it a few times, found a determinant. But then it's like, well, how do you unfind the determinant? Right? Now, the reality is you don't unfind the determinant. You find the determinant just using it for a different reason because you would have the A and B and you would be using an inverse matrix multiplication to figure out the other vectors. But they're totally working backwards to arrive at these rules that exemplify what this relationship is, just so we could use matrices to be able to evaluate something that is very, seemingly very complicated. All right, it's a pretty crazy looking stuff. Oh. Yeah, we actually want stack calc 8 because it's in the form of a plus bx. So I wrote my. I hate myself. I couldn't make it through a problem without screwing something up. So apparently before I handed out the new packet to you, I made some edits. Or was this edit in your packet? Yeah, with plenty of space to do. I really hate myself.
If it just squeezed.
Just right on the other side.
Yeah, there it is, like right here.
Oh wow.
So I mean, so pretty straightforward problem in terms of like the level of difficulty because there really isn't that many points. And when there aren't that many points, that's generally a good thing because if we have to do all these calculations, if I handed you a data set that had 300 values in it, that would be a problem. Even if you were using the native function in the graphic calculator to do the linear regression, once you get past like 20 ordered pairs, it starts to beg the question, like, why are we doing this? Like we should be using Excel. We should be using something that is capable of handling large data sets. All right, but when you're looking for least squares line, really, I mean, it's just following this process. So we don't have to invent these formulas in order to use the approach. All right, so we're going to use matrix operations to figure this out. But like I said, I'm also going to show you how to do it on the calculator if you don't already know. All right, so first thing I have to do is identify my X matrix, which is all the X values, so 1, 2, 3, 4, and 5 down the second column, because the first column is all just ones. I like to put the second column in first, because if you take a quick glance at it, you don't always know how many ones you're supposed to put in until you put the corresponding X values. All right. We don't have to actually write out what the X transpose is going to be, because the calculator can do that for us. All right. We do need the Y's, but that's easy enough. Just a simple list of the Y values. 1, 2, 4, 4, and 6. All right. So not a trick question, but I could see how people could get tripped up on something like that. You know, like on a test. You know, like your brain is telling you, yeah, it's 1, 2, 3, 4, 5, and 6 again, but I would question that, because why would I ask you to use a regression technique if all the points fell on the same straight line? You just do a little change of Y or change in X and call it a day, you know? So something's got to be a little out of whack in order for this process to really bear out. All right. So I'm going to need a 2x2 matrix, AB, and then another matrix, but this or vector matrix, which is going to be a 2x1. All right. All coming from these two matrix or vector matrices. All right. So edit. This is a 5x2. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. Quit out of there. And then our matrix B is going to be a 5x1. So that's going to be 1, 2, 4, 4, 6. 1, 2, 4, 4, 6. All right. So you just don't want to lose sight of what or where you stored your matrices. All right. So I'm going to do the transpose of matrix A. Into the matrix editor, go to math and select option 2 as transpose. Put the multiplication symbol in or not, it won't make a difference. Shouldn't make a difference. We're multiplying that by matrix A. All right. So that gives us our first entry. 5, 15, 15, and 55. All right. What I'm going to do is store that in as matrix C. Because I don't want to lose that. I'm going to need that again in a minute. All right, the other calculation is the transpose of A multiplied by matrix B. All right, so I'll recall this and just wipe out the A that I multiplied by and actually multiply it by B. All right, so transpose of A multiplied by B, 1763. And so what AB will be is the inverse of this matrix which I have stored in matrix C, and the 1763. Now, if you're worried that you're going to lose that new matrix there, store it in as D. All right, so now matrix C is this guy here, and this is my matrix D. All right, so originally we had matrix A and matrix B. All right, we ran our calculations and we stored it as we went. So as long as I find the inverse and multiply, I'll have what I'm looking for. All right, so matrix C inverted times matrix D. And so we get that. And you can convert it over to fraction form, but if you know anything about correlation and regression, decimals are kind of the order of the day. So negative 0.2 and 1.2. The fact that we actually got clean decimals, relatively clean decimals, is somewhat surprising because that's not typical. All right. So it said, the question said find a least square line or least square regression line, linear regression equation, line of best fit. It all means the same thing. That's always in the form of y equals ax plus b. Right? It's not always in that form, but that's the most useful way of representing it. So therefore, we're looking at y equals negative 0.2x plus 1.2. So using matrix operations, we're able to find the line that best fits this data set. All right. So let me show you the other way. And this other way is not how you're going to do the problem. You're going to do the problem this way on the test. The other way is how you're going to check it and make sure your answer makes sense. All right. And I'm also going to create on the fly a new example. Oh, I love myself sometimes. I created the new problem already on the fly at one point, and here it is.
Is quadratic regression another phrasing for the least squares?
It's a manipulated form of it. So we're going to have to tweak our stuff here in order to get what we're looking for. But yeah, apparently that's the thing. So in the stat editor, we're going to just type in this data set. There's a raw set of data points. So stat edit. If you have any data entries, because I don't know how familiar everybody is here with the stat editor, you know, we might have, honestly, I'm getting all my classes confused with one another these days, so maybe we did, maybe we didn't, but I'm going to assume that we didn't. If you have data entries in there, just clear them out. The way you clear out data from a list is just by hitting clear and then enter, all right? And it'll wipe it all out. You don't want to hit delete on a column heading because then it'll delete the column heading also, and you'll lose the ability to recall L1 and L2, all right? So the X values go into L1 and the Y values go into L2. You might find it surprising, but behind the scenes, the calculator is doing what we just did in order to find the least squares regression line, right? So it's just not showing us those steps. It's just saying, oh, wow, I will happily compute the linear regression equation for you. And you say, okay, great. But behind the scenes, it's doing what we just did. I missed something. 1, 2, 4, 4, 6. Okay, so that's fine. So I typed in a 6 in the last one for some reason. All right. So you get your data in, quit out of there. I just quit out of fear. Well, between matrices and lists, I quit out of fear that I'm accidentally going to type the next function in as an entry in the list. All right, so stat calc option 4 is going to most closely align with the solution we just came up with. Because there's an option 8, which is a different type of linear regression. I mean, it's the same linear regression, it just reverses the coefficients A and B. right? It makes the A the fixed quantity and B the variable. You want option 4, all right? And then you just tell it what the lists of data are, L1 and L2. Oh, I was like, is that phone? That's crazy. List 1, list 2. You could store the regression equation if you want, but we don't really need to do that, so we're not going to. At least not yet, not till we get to the next one. And then you go to calculate, and it'll give you the line of best fit. And if your calculator is set to the right mode, it'll also tell you the correlation coefficient. So it gave us what we expected. Oh, it gave it to us backwards. All right, let me look at my equations. Double check. Maybe my equation is better. A plus bx. Guess I changed that on the fly too. So y would be equal to 1.2 minus 0.2x. Right? It calls for the fixed quantity first and then the variable quantity. Right? So you can still get what you need out of this. It's just it's going to be, the A's and B's are backwards. But the better way to do it would be to use, so disregard what I said before, use stack calc 8. All right, so we'll just do it again. Stat calc option 8. And you can see it's the same structure, L1, L2, and then calculate, and then you have it. All right, it does not impact the correlation coefficient. Just a word about that. Some of your calculators will not show you the correlation coefficient unless you turn on your stat diagnostics. All right, so you can do that if you want, but we don't really need it. All it does is it gives us a sense of the strength of the relationship between the two variables in a linear fashion. All right, so this is saying that there's a very strong linear relationship between the two variables. All right, but you can tell that visually. If the points, when plotted, look like they would form a straight line, or at least close to a straight line, then you would expect this to be a strong value. One is the perfect. All right, 1 is perfect in the positive direction, -1 is perfect in the negative direction. All right. So the second example is talking about a quadratic regression. All right, so for this, we have to do a little bit of manipulation. All right, so what we have to do first is find a quadratic transformation. All right, well, it's really a linear transformation, but in a quadratic sense. All right. So what we have here is a list of x and y values. So I'm just gonna list out the raw values: 1, 2, 3, 4, and 5. One, 2, 4, 4, and 6. All right. So what we want to do is we want to transform this into a linear relationship from what would be a quadratic relationship. All right. So that is not a highlighter. We're going to manipulate these y values before we even get started. All right. So these y values, I'm going to find the square root of each one of them. So basically, we're going to do the opposite operation. I don't know why I put the radical around the 1. All right, we're going to find the square root of each of those y values. All right, so what we're doing is we're scaling down. It's basically, if you've ever experienced something called a log scale, if you've graphed on a log scale, what that is it's manipulating the y-axis to go by logs instead of by actual numerical values. And so everything appears to be linear, right? So what we're doing is we're changing the y-scale to, instead of going by y values, we're changing the y-scale to go by the square root of y.
That's red 6.
Red 6, thank you. back on track. I don't like making it through a problem without making a mistake. Doesn't feel right. All right. So we'll have the same x and x transpose that we had before, because nothing changed there, but our y vector is going to be different now. All right. So x is still going to be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But now y is going to be equal to 1 root 2, 2, 2 root 6. All right. So just to kind of answer a question that may not be pondered just yet, if I wanted a cubic regression, you'd find the cube root of all your y values. If I wanted, any polynomial, that's what you would do, right? You're always going to do the inverse operation, right? So if I wanted to find a sine regression, you'd find the inverse sine of all your y values, right? So always the opposite of whatever it is that you're looking for, right? The inverse operation. All right, so the reality is all I have to do here in order to carry out this process is go into my second matrix, because the first one's fine, and just make all these radicals. It's going to convert it to decimal form, but you got to do what you got to do. Because essentially what we're trying to do here is fit a parabola to a data set that actually is fairly linear. So we're not expecting nice numbers anyway, right? That ship has sailed. Right, but the good news is, or some of the good news is, we could rely on a lot of the same stuff that we did before. I need the transpose of A multiplied by A, right? So that's exactly the same, right? So if we go back to what we did before, here's my matrix A, and this is my matrix B. It's same, all right? For at least for X transpose X, all right? So the left-hand side is going to have the same entries. Against AB. Things start becoming a little different when we work on the other side, which is the transpose of X against Y. All right, so I'll just find that calculation there that we did before and do it again. All right, so that's pretty nasty. All right, so before where it was kind of a luxury to store it in as a new matrix, now you just want to. All right, so this, I'll write it as an approximate. So I'll say it's approximately equal to 8.9 and 30.1. All right, so this got stored in as C. I didn't change that from before, but I definitely want to store this in as my new D. And that's not how you store it in as D. So store it in names D. All right, so that hideous decimal, as ugly as it is locked in there for D. All right, so AB. Now this is going to give me a linear equation because we're following the linear approach. It's what we do with that that's going to make it quadratic. All right, so inverse of C against D, which I'm sure I have in here somewhere. There you are. Is that. Oofa. Pretty nasty. Right, but there's no way around it. I need those entries. Right, so I mean I could store it all I want, but I need to write them down somewhere. So 3 decimal places is fine. So 0.727, 0.348. So what this gives me is the line that best fits the data set where X is the values from 1 to 5 and Y is 1, rad 2, 2, and rad 6, so the square root of the true y values.
How did you get D again? I'm just having.
Product of the inverse of C and, oh, the D, this one here, that's the product of transpose of X and Y.
Okay, alright, okay. Y from this,
Our new set of Y's, yeah, which is B.
okay.
So A transpose times B. All right, and so what we have here is the linear equation y equals 0.727 plus 0.348 x. All right, so again, it's the y equals a plus bx, as annoying as that is. All right, but you got to remember, previously, in order to get this, what we had was the square root of y in my L2. All right, so this really isn't a y.
AX plus, isn't it AX plus B?
I was mistaken before, but you had stepped out. So it's actually a plus bx, and it's stack calc 8. So the general model tells us that it would be y equals a plus bx. However, we didn't do this for x against y. We did it for x against the square root of y. All right? So that's what we really got out of all of this. All right? That's not what I want. I mean, it's equivalent to what I want. Instead, what I want, though, is what y would be equal to. Y would be equal to, if I square both sides, 0.727 plus 0.348 x as a quantity squared. And so what we did was we used a linear regression technique to come up with a quadratic model that would represent the data set. All right? So, yeah, it's one of those things where, is it going to be a good fit? Well, it's not going to be probably as good of a fit as the linear equation, but I wanted to keep the example relatively simple. So what I'm going to do just very quickly, and this is not anything that you would have to do, I just want to show you what the stat plot would look like, and then show you what this graph would look like in relation to that. Actually, both of them, just so we could do a little compare and contrast. All right. So L1 and L2 scatter plot graph. I can turn off that function. So this is what my scatter plot would look like. All right. So loosely linear. Pretty safe bet that it's a linear relationship. You know, like if you were presented a graph that looked like that, and it was a multiple choice question and said which of the following would be the best fit, a line, quadratic, trig function, or an exponential function, you look at the picture and you say, all right, maybe I make a case for a little wiggle in there, so maybe a trig function, but I'm going with the line. I'm going with the safe bet. All right. So I'll put my linear function in, which is 1.2 minus 0.2x. You could actually have it stored in there, but it's a simple enough equation that we don't have to worry about it. All right, graph it. Okay, so I screwed up something.
That's the old equation.
Oh, you know what? It's funny because I corrected this from the wrong answer to a different wrong answer. I can't get out of my own way sometimes. Which is why I have these vague descriptors for all these videos when I post them online, because I don't need people saying mean things to me that are strangers. Negative 0.2 plus 1.2x. Because it's a plus bx, and there's my a, there's my b. It's like right in front of my face, but still somehow I screw it up. But it is coming down to the end of the course, so we've made it this far. All right. Well, just by looking at it, you know, once I hit graph, I knew it was wrong because it had a strong relationship, and it didn't look like it passed through any of the points. This one at least does. All right, so pretty solid, right? Now, let me take a look at the other one and compare. So 0.727 plus 0.348x as a quantity squared. All right. So in either case, you could say, okay, yeah, I see it. You know, like this parabola was fit in such a way that it's, you know, a parabola exists in a whole lot of other locations, but it's sweeping down and it's coming up and grabbing these points along the way. All right, so context is going to be the deciding factor when deciding or determining which of these to use, because, you know, sometimes a quadratic makes sense, sometimes it doesn't. I mean, if you're talking about P waves and S waves for an earthquake, right, they're quadratic in nature. So then it would make sense to use a quadratic function. But if you're talking about, you know, a person's income over time, quadratic would not be appropriate. Right? I don't know that you necessarily want to go with linear either. Maybe that's the case for exponential, logarithmic. You know, the growth of a human over time may seem very linear early on, but then after a while, it starts to level off. And so in that case, you start getting into a logarithmic relationship. But it's very easy to carry out this process once you identify what the technique is going to be, because again, it's really just letting the calculator do the heavy lifting for you. Right? You just need to identify your X matrix and your Y vector. As long as you represent that vector appropriately, you're going to be in good shape. And as long as you know that whatever it is that you're trying to do, because really we're using offsetting approaches here, because there are quadratic regression techniques and cubic regression techniques and quintic regression techniques. But why would you do that if you could just use the inverse operation here and then correct for it down the line? All right, so that's all we're really asked to do, or trying to do, so why not just do it that way? So if I needed, like I said, a trig relationship, I would find the inverse sine of this, and so I'd have the inverse sine equal that. I take the sine of both sides, now I have a trig function. All right, I could do it with pretty much anything. The caution is it has to exist for the values that you're using. All right, so if I try to do an inverse trig function with this, I could run into trouble if I have domain considerations, right? Because when you're talking about like the inverse sine, you know, like inverse sine is going to be related to a ratio. You know, that ratio needs to be between -1 and 1, right? So that wouldn't work out for something like this, but maybe an inverse tangent, you know, something along those lines, all right? So a lot of different applications for this, but basically it's all related to two variables. If you can have two variables that are related to each other in some way, you can apply a regression technique. This is really just showing you how it all works, right? So you get into a lot of that stuff in a stack class. So that's probably where the biggest extensions exist.